Hi, everyone. Welcome to today's webinar. I'm Meredith Kenton, MEGGER's Digital Marketing Specialist, and I will be moderating today's presentation. I will be asking or reading the questions to Jeff at the end and helping along with any technical issues. So on your screen, you should see a panel on the right that looks similar to this one. We ask that you send in your questions and comments during the presentation, and then at the end, we will answer them for you. If your question isn't answered at the end, you will receive an answer via email after the webinar ends. And then today's presenter is Jeff Jowett. He is our Senior Applications Engineer. His contact information is right here if you'd like to reach out to him directly. And he's been with MEGGER for 39 years, and he's truly an expert in ground testing. Let's get started.
Okay, good morning, everyone. Thank you, Meredith, and welcome to our introductory course on ground testing. Now, this whole topic would take a whole day and then some to really cover. So this morning, we're just going to look at the fundamentals of the subject, and over the next few weeks, we will be presenting additional webinars that go further into it. So if there are things that you're interested in and you don't see them this morning, just watch our information that we'll be sending to you on the additional webinars, and you'll be able to, over the next couple of weeks, pretty much cover everything. Okay, next. I want to start with a very fundamental issue. What is a ground? And basically, we're talking about an electrical connection. It can be inadvertent, but for the most part, we'll be looking at deliberate electrical connections to the earth or to the ground. And the most common thing that people think about in terms of grounding, of course, is lightning strikes. You want to divert this out of your system and try to just get it quickly and safely into the ground and let it average out. Also, a huge source of problems are fault currents that occur on the utility. And so again, we want to divert these out of your electrical system. And there are also some more subtle, less well-known issues that can maybe not burn down buildings or kill people, but can cause very serious problems on your electrical system. And this is things like static and noise and so forth. So a good ground is there to divert these currents that you don't want going through your electrical system. You want them going back into the soil. And in the case of utility faults, they go back to the transformer that generated them in the first place. In the case of lightning, of course, the charge evens out between the earth and the sky. Okay, next. So what are some of the benefits? Why do we want to make sure that we have a good and proper grounding system? Well, paramount, of course, would be to lessen the chance or eliminate the chance of injury to humans through electrocution or shock. Also, of course, you're minimizing the likelihood of damage to from lightning strikes to and also utility faults. You can figure into that as well, to your equipment. And then the one that is overlooked to some extent, but is becoming more and more important, is the performance of sensitive equipment. Computer and communication circuits and so forth that are operating on a couple of volts. And if you don't have good grounding, you can develop serious noise problems. Next. And we'll start with a quick look at the history. MEGGER has been involved in the production of ground testing equipment since day one, so to speak. MEGGER invented the insulation tester back around the turn of the 20th century, And then from there, they took that basic fundamental idea and then continued to modify it into other types of electrical tests. And so one of the first ones that we branched into was ground testing. Dr. George Tagg was a MEGGER employee back at the beginning of the 20th century, and he is one of the pioneers in laying the groundwork for how do you do good grounding and how do you test it. And it's interesting, those of you who are interested in this sort of thing, to look into, well, how did they take, let's say, the basic circuitry of an insulation tester and modify it into being able to do a ground test? And that's exactly what they did. So they went from high resistance and high voltage down to low resistance and low voltage, and modified it so that you could use a tester to test the efficiency of your grounding electrode. Next. And it's just a quick look at the old time applications from many years ago. And some of you might be familiar with the tester that's shown on the left is an old null balance technology that was made by us. And I think probably a few of these are probably still being used. If you have one, and as long as it's in calibration, there's nothing wrong with using it. The main thing to think about here, or to focus on here, is these old testers gave you perfectly good information as far as making the measurement that you're looking for. But over the years, the improvement has come in all sorts of additional functions like the safety, the speed, the accuracy, the reliability. All sorts of convenience features have been added steadily into these testers up to what we can now offer you today in a full-featured ground tester. Next. So we'll look at some of the earth testing theory and what's behind the fundamentals of the tester and performing the test. Next. So there are two basic types of measurement that we're going to be looking at this morning. And so we want you to come away with an awareness of the differences and the similarities and where the two different types of measurements apply. There is resistivity and there is resistance. And the terms are very similar, and they do sometimes get confused in dialogue, but they're quite distinct and quite separate. And so we want you to be aware of the difference between the two types of measurement. Resistivity pertains to the electrical properties of the soil itself, independent of any human intervention in terms of an electrical system. It's just how well does the soil conduct electricity and how good is it for grounding. And then resistance has to do with now you've installed the electrode, and now you want to be able to measure how good is the electrode, how well can it do its job. And so that would be your resistance measurement. Next. So we'll start now with looking at resistivity. Next. Okay, why do we want to measure resistivity? A ground tester will typically do this. And what is the purpose of it? Well, for one thing, if you do have the luxury of additional space to work in, if you're making an installation and you want to have the best possible ground, you can actually prospect a piece of ground and find the lowest resistivity, which would be the best place to install your ground. And more in a more practical sense, or used far more often because most people don't have a lot of room to work in, you can also get values of the soil resistivity, which are critical in designing a ground system. And we'll talk about that a little bit. And be aware that resistivity is referred to in the literature as a constant because that's general terminology. That's all that is. But it really isn't very constant in the practical sense. It depends enormously, first of all, on earth composition, and then also on things like moisture and temperature. So you'll find that resistivity varies from down around 100 ohm centimeters up to nearly 1,000,000. So that's an enormous range in which different types of soils will fall depending on how well they can conduct electricity. So that's your earth resistivity based on earth composition. And then it also varies tremendously in terms of the moisture. Your ground can be very good in the spring and not so good in the hot, dry summer. And temperature also has a notable effect on your ground. So we'll talk about how resistivity varies throughout the year. One important thing is to water table. If you're installing a ground, now deep-driven grounds are expensive, and so you may not have the luxury of doing that. But if you do, if you can hit the water table, you can establish a pretty reliable, steady ground through the year by tapping into the water table. And those of you who are up in cold climates, keep in mind, get your ground below the frost line, because in the winter, if the soil freezes, then the resistance of your ground will skyrocket and you won't really have a good ground anymore. So get that below the known frost line for your area. Next. Okay, so this is the fundamental schematic for testing soil resistivity. This is the Wenner method. Now, there are other methods adapted for difficult situations, but the most commonly one used is the Wenner method, named after Frank Wenner, who was a pioneer in this area in the early part of the 20th century. And for this, you have a 4-terminal tester. So we show 4 terminals here, 2 currents on the outside and 2 potential terminals on the inside, hooked to the tester's measuring circuits. And so for this type of measurement, you must have a 4-terminal tester. Now, ground testers come in 3-terminal configurations and 4-terminal configurations. Now, either one will do a resistance test of your electrode, but in order to do resistivity, you must have 4 terminals. So if you're buying a tester, just look into your crystal ball and evaluate what you may be called upon to do. 3-terminal testers are a lot less expensive, and if you're sure that you're only ever going to have to test grounds that are already installed, then you can save money and you can buy a 3-terminal tester. But if you're going to test soil, if you're going to get involved in installing or designing a new ground, you must have a 4-terminal tester. So what we see here is a Kelvin bridge type of measurement. 2 terminals on the outside inject a test current through the soil, and then 2 terminals on the inside measure the voltage drop caused by the resistance of the soil, and the tester gives you a number. And then you plug that into the Wenner formula, which we see down here, 2 pi AR. So let's see, I guess we can go on to the next slide at this point. Okay, so A in the formula is the distance between the spikes. And what you'll be doing is measuring average soil resistivity to a depth that's equivalent to A. So the 4 terminals are equidistantly spaced. And that spacing you plug into your 2 pi AR formula. And R, of course, is the reading that you've gotten off of your tester. And then when you plug that into 2 pi AR and calculate that out, that gives you your average soil resistivity to a depth equivalent to A. And note, we show the probe depth as being 1/20th of A. I want to comment on that because it's relatively important. How far do we push our probes into the soil? Well, for the Winter formula to work perfectly, he noted that a lot of additional terms dropped out if you used a 1/20th of A probe depth. And so that averaged out then to the 2 pi AR relatively simple formula. But I've spoken to many people who do resistivity testing, and they've all told me that they don't really bother all that much with 1/20th being that precise. They just push the probes in and get a measurement. So I'm guessing here that the error that's introduced by departure from the 120 depth isn't really that significant. It isn't really that large. So in practical field testing, apparently you can just push your probes in and get a measurement. But if you're trying to be perfect, then adherence to the Winter method does say that you push your probes in 1/20th of the depth. Okay, next. And you can also work backwards then from the Winter method and get a number for R, meaning the resistance that you want to have to your grounding electrode that you're installing. You can work backwards and you can get a number. And the important thing here is that you can get software from the companies that sell grounding materials. So this would be like Lincoln or Hogger Lightning Protection. Companies like that typically will provide you with software, and you can plug in this relevant data, like the R number that you're trying to achieve, and also your soil resistivity for your local site. And the software will then design the system for you, and it will tell you, okay, you want to have 20 10-foot rods in order to reach a resistance of such and such a number. So this is where you can use this type of data to design your grounding system. Next. Okay, that's resistivity. Now we'll move on to resistance. And this would be your system has now been installed and you've got your electrode buried in the soil and you want to test this. Next. We'll take a look at some definitions and of course the important factor of why do you test your grounding electrode, and we'll look at some of the component parts of a good ground electrode system and its intended resistance. Next. There are two types, we can kind of look at this in terms of two types of grounding electrode. The simple, which everybody typically thinks of, just a rod driven into the ground and your electrical system tied to that. But there are also very complex systems that consist of arrays of many driven rods paralleled together, or a grid or a mesh. And the main thing to remember here is that for testing, these things are pretty much all the same. You don't need some kind of special, if you have a large grid, quarter acre or whatever, and you want to test that, you really don't need some kind of a specialized tester to deal with that. A standard ground tester will test that. The big difference between simple and complex grounds as far as testing them, the big difference has to do with procedure. not with the tester. Next. Okay, why do we want to test our system? Okay, why do we want to test? Now, excuse me, I'm getting interference here, but okay. Why do we want to test? We want to enable the protective devices to operate. So your grounding system is paralleled in with your neutral, and so it gives you an added redundant protection for the operation of your protective devices. And we want to limit ground potential rise. Excuse me for that little break there. We want to limit ground potential rise. And for that, let's go to the next slide and I'll talk about that in a little more depth. We see the terms in the literature: step potential and touch potential. And so these are primarily relevant to substations, but also can be applied to industrial facilities and so forth. This is a protective device. We don't want our equipment, in the event of a fault, to have a potential rise so that a human who touches usually something metallic, a machine or whatever, we don't want the human to in turn become a part of the across the potential to ground and develop a current. And so what we see here, step and touch voltages. A step voltage would be the voltage that you can develop between your feet while you're passing a substation. And what will happen then, if a fault is occurring, of course, then the fault current is trying to go back to where it was generated, the substation, and as it gets closer and closer, it of course becomes concentrated and can produce a higher potential to a human being in the vicinity. So 3 feet is about a human stride. So a step potential would be the voltage that you develop between your feet if you were walking by, and similarly, a touch potential being if you touch the fence. So in order to limit that to a safe voltage, you can perform a step potential test or a touch potential test. Excuse me just a moment. My apologies to the attendees. We're working remotely because of the coronavirus, and so there is a certain level of interference that we have to overcome. Okay, so you would connect your tester to the substation ground, the current terminal, one current terminal, and then the second current terminal is out to a remote point with a spike driven into the ground at some remote distance. And then you have your potential terminals going either to 2 probes in the ground 3 foot apart to measure step potential, or one potential going up to the fence of the substation and the other one to a probe about 3 feet away in the ground in order to measure touch potential. And with that, then you can get the resistance measurement and then plug that into Ohm's law and calculate out what the voltage would be in a maximum fault situation. So the current that you use in Ohm's law would be the maximum fault current that could occur. And you want to then have your voltage lower than 50 volts for human safety, or now it's becoming somewhat more rigorous, and so sometimes you'll see 40 volts in the literature. And then this idea, of course, is applied in general, that you don't have the possibility, your good ground will limit the possibility of a high potential rise developing across your equipment inside a facility as well as around a substation. This is just an illustrative slide. Okay, next. And this, for those of you who like graphic representations, this just portrays the same idea in a graphic form, the idea that as your current goes to zero, your voltage rise levels off and becomes steady. And as I said, in the case of safe ground potential rise, you want to keep that below at least 50 volts and maybe 40 in some more rigorous environments. Next. Okay, let's take a look at component parts of a ground electrode resistance. Now, this shows a simple ground rod, but everything I'm going to say pertains to, if this was a quarter-acre grid, everything I'm telling you is going to pertain just the same. A ground is a ground is a ground. It doesn't make much difference if it's a rod or a large system. Okay, so there's the resistance of the electrode itself. This can be discounted because that's a large metallic object. Now, the contact resistance between the electrode and the surrounding earth, you might think this would be a problem, but as a rule, it isn't. The fault current is able to transfer pretty well from the rod over to the surrounding soil. So the component that really we're concerned with then is the resistance exerted by the surrounding soil to the flow of the fault current. And we can think of this, just for illustrative purposes, we can think of this as if the electrode is surrounded by shells of earth. So immediately the first shell would be relatively small and would exert a resistance. And then as you go further out, there's more resistance exerted against the flow of current. But the critical point to remember here is that the current is not flowing in a straight line as it does in an electrical system through wires or rather, the current is able to disperse 360 degrees around your electrode. So as you encounter more the transfer soil as you get further and further away. So the resistance, the additional resistance is becoming less and less. And at some point, there is so much volume of soil that there's no additional resistance exerted. And so that's the point that you're looking for. You want that to be a relatively low number. And so as we test for the grounding resistance of your electrode system, we'll see how we determine that and how it's applied. Next. Okay, so we're measuring the grounding resistance then to determine its value and how we apply that then to evaluating the protection of our electrical system. And there are different methods. There's a future webinar a little bit in a week or so away where we go into all the individual methods. So we won't cover the methods too much today, just in an introductory form. We're going to take a look at 2-pole measurement and then 3-pole measurement. The slope method, we won't go into that today. That'll be treated in the future. But the slope method is a means of working in very tight environments. And then there are also some additional technologies that could be applied, the ART method and the clamp method. That's for a future webinar. We will describe those technologies in the future. Next. So we'll start at first by looking at what are the values that you look for. What constitutes a good ground? The most prevailing value is 5 ohms. So for typical industrial and commercial grounds, you want to see at least 5 ohms. That's a pretty prevailing industry standard. And then when you get into more demanding environments, you'll typically want to have lower values. So a chemical plant, for instance, they want to make sure they have to worry about sparks developing or arcs, which could cause explosions. So they want to have typically a lower resistance, 3 ohms, a typical value. The same thing for things like computer systems, where they want to eliminate noise because that's a huge problem in sensitive equipment. So again, they would have a lower ground resistance. And then substations, of course, are the most demanding, and then they typically want to have them under an ohm. Now, I want to just make reference to the only really prevailing standard that you'll see kind of in written form is the 25 ohms. You'll see that all the time in the literature, very frequently in the literature. That comes from the National Electric Code, 25 ohms or less. Bear in mind, that is a very forgiving standard. The electric code, the National Electric Code, is concerned with safety, with shock and fire. It does not concern itself with good performance. And it says that in the preface or somewhere. So the 25 ohms is a forgiving standard. It is not really a good standard for commercial and industrial. You want to have a much lower ground resistance for those types of applications. Okay, next. Then we'll take a look then at the 2-pole measurement. This is basically where you have shunted the terminals, either 3 or 4, on your ground tester, and you've shunted those into a 2-terminal configuration, and you're just running a wire out to a convenient low resistance return, which typically is the water pipe system. And in this configuration now, the water pipe system, or something like a metal fence system, can also be used. The idea is that's an electrical connection, and this procedure is typically referred to as dead earth. And what they mean by that is the return is not part of any electrical system. The water pipe or fence is not part of an electrical system. So in that respect, it's dead. And so you see the term dead earth in the literature. And so this is a 2-point measurement where your test current is now going from your electrode that you're measuring through the earth out to some arbitrarily selected point of return, such as the water pipe system. And what you see on your display then is a loop resistance of this whole electrical loop, and you're counting on that being mostly the resistance of the earth. And you're counting on your return, such as the water pipe system, as contributing relatively little to the measurement. Okay, you can do this. And it's basically a drop dead type of measurement for situations where you just can't do a conventional ground test, usually because you're in a very crowded environment, such as an urban environment. and you need to have something to at least give some idea of the resistance of your local ground. And so the dead earth or the two-pole measurement, it is described in the IEEE 81 ground testing standard. It's a better than nothing type of test. It's not very accurate. It's not terribly reliable, but yes, you can use it in an extreme environment where you don't have any other option. Okay, next. And well, we'll see here what are the limitations of that, which I have pretty much already described. So these are pretty apparent. Okay, next. So now we're taking a look at the best way to do a ground resistance measurement. The two-pole is cheap and dirty. The three-pole is now the really good, reliable way to do a measurement. Now, you can do this with either a three-pole or a four-pole tester. But what we're showing you here is if you had a three-pole tester, you would hook your common to your ground that you're testing. Then you would take your current terminal and you would run a long lead and a probe out into the soil. That sets up your test current. When you energize your tester, that puts your test current through the soil. And this typically applies a square wave current so that your tester can recognize your local current, your applied current, apart from the noise that's traveling in the soil. So a ground tester is not a DC test. It's a square wave test so that the measurement circuit just looks for the test frequency that the tester applied. And then your potential terminal is connected to another probe somewhere in the direction of your current probe, and it looks at the voltage drop caused by the resistance of the soil to that point. So now the tester knows what the current is, it's measured what the voltage is, and it applies Ohm's law, and it gives you the resistance to the point where you placed your potential probe. And that's pretty much the fundamental of doing a ground electrode test measurement. Next. Okay. And so the procedure then is that you will now vary the position of your potential probe, and you're going to walk the potential probe in a series and take a series of measurements going out towards your current probe, and you're going to plot those measurements against the distance at which the probe was placed. Next. So this is what we're looking at now. The current probe placed remotely, potential probe somewhere in between. And the dotted lines represent the electrical fields associated with this test. So there's an electrical field around your test ground that maximizes at some distance. That in real good soil, that could be like 10 feet. In real bad soil, that could be half a mile. You just don't really know. But it maximizes at some point. And then, of course, your current probe, because it's doing kind of the same thing, it's injecting current into the soil. So the current probe has its own electrical field around it. And you want your potential probe somewhere in between. Now, I should comment quickly that you can do this with either a 3 or a 4-terminal ground tester. And if you have a 4-terminal tester, the operator has the option of shunting that into a 3-terminal position and using 3 leads, or he can keep it in the 4-terminal position and run two leads, a current lead and a potential lead, over to your test ground. The only advantage you have of doing that is if you run a 4-terminal configuration, then that's a Kelvin bridge, and it eliminates all of the lead resistance from your measurement. Now, in a 3-terminal position, then you do get a little bit of lead resistance from your common lead going from your tester to your test ground. That enters into your measurement. It is normally very little and can be disregarded, but if you're trying to measure a very low resistance ground, like a substation under an ohm, then sometimes it's a little more convenient to do the extra work if you have a 4-terminal tester and run all 4 terminals to your 2 of them to your test ground, and then of course your current and your potential probe. It makes the measurement just a little bit more precise, which can be helpful in a very low ground measurement. Okay, next. So this shows you then what you're basically going to be doing is plotting and taking your measurements at a series of positions and then plotting them against the distance, and you hope that you will get a graph that looks something like this. You have the resistance rise in the electrical field of your test ground, then an area where that remains relatively constant because you're distant from your test ground, and then starts to rise again as you get into the electrical field of your current probe. Next. So now we're going to just take a look at how you would be actually performing this test. Your operator is walking the probe and taking a series of measurements. Okay. Next. And at the end, you're looking for this area where it remains relatively constant. And if that happens at 2 ohms, you've got a good ground. If that happens at 50 ohms, you don't have a good ground and you need to do something to improve it. Okay, next. And you will see in the literature very often 62%. And we won't go into that today, but if you take the webinar for the different methods, then we'll elaborate on that more fully. And now the next question then becomes, okay, how far out should my probe be? Well, you'll see tables in the literature, and they tell you based on the size of your electrode. The tables will tell you how far out to put your current probe. There's different ones that you see in the literature. Very often you see 5 times maximum dimension. So this would be if your current probe, if your electrode was a 10-foot ground rod, you would go out 50 feet with your current probe. Of course, with larger systems, then you measure like a grid, you measure the diagonal and then a multiplier of that. But the thing to remember here is that these tables are not scientific demands. They are simply suggestions that give you a pretty good chance of getting a nice test result on one try and not having to keep repeating it. If you don't have that distance, if let's say you calculate out against a table and it tells you, well, you have to go out 500 feet with your current probe, and you don't have 500 feet, you have 350 feet. Okay, do your test at 350 feet. If you get a good result, you're good. Don't worry about it. You've made a good test at 350 feet, and that's fine. So the tables are just suggestions. They are not scientific demands. Next. This is the one real problem that you do not want. This is where your current probe is too close. and its area of resistance overlaps with what you're trying to measure. And if you graph this, you wouldn't be able to tell where the resistance of your test ground maximizes and stops. So in this case, you'd have to go out further with your current probe. Now, we're not going to go today into depth on this, but on the upcoming webinar on methods, we'll teach you how to deal with that. But you would have to move, in this case, you'd have to move your current probe further out and retest next. Okay, so fault potential, it's your best method. It's extremely reliable. It conforms to IEEE. The operator controls the test. It's a very good method, but it does have limitations. Next. It's time consuming. You're making a lot of measurements, and it does take up a lot of time. So next, we'll close today with a look at the next procedure, which is simplified fall. And this helps you to do the reliable test in a shorter time. Next. Simplified fall has the advantage that it's not as much work, so it's quicker, but there are more variables, so it's a bit less accurate and reliable. Next. And in simplified fall, you're only taking 3 measurements. You're going to take a measurement halfway the distance to your current probe, and then one 10% in and 10% out. And then you'll see on the left there a mathematical crunch. So those 3 measurements are R1, R2, and R3. And you're going to plug them into that little mathematical crunch. And what that does is calculates out the percentage error for the average of the 3 measurements. And so if that calculates out to a nice percentage error, like, 2%, that's pretty good. And so you can say, okay, I'll accept this measurement, the average of those 3. If you get something like a 10% error, well, you wouldn't buy a multimeter with a 10% error, so you won't accept that. So you'd have to go back and retest and do something more rigorous. But the idea is behind simplified fall, you could save time. And now the obvious question here is, well, suppose I just looked at the measurements and made a decision. Well, yes, that's what a lot of veteran operators do. They don't really bother with the math. They just do what you could call the eyeball method. They move the probe back and forth, and they look for the conformance between those 3 measurements. Well, if they're all exactly the same, you're really good. But in most situations, they won't be exactly the same because of soil variance, especially at graded sites. You have different types of soil at different spots. And so usually the 3 measurements might vary a little bit. And so the operator can just say, oh, they're close enough. That's good. I'll accept this. And this is what a lot of veteran operators are actually doing. But if you have to submit your test result to a third party, it's a good idea to have something objective to submit. So then do the math and submit your result, and you're good to go. Next. Okay, with that, we've reached the end of the presentation. Like I said, you have other webinars coming up that will go in more depth. I apologize there was some interruptions going on here for technological reasons. I apologize for that, but it's question time.
Okay, so Jeff brought up a good point. If you guys are interested in seeing all of the webinars we have planned, you can go on the us.megger.com website, and there is a tab at the top that says webinars, and that has the full schedule of all of our upcoming webinars. Okay, so the first question is getting ground rods below frost level sufficient, or should entire ground grids be below the frost line?
Yes, you you should get the entire grid below the frost line. However, of course, that could be very expensive. So a lot of grids have rods associated with them, and in that case, yeah, uh, if the rods are were deep driven, and you test the system, and it comes out, gives you a good resistance test, then you're okay. Not the mesh doesn't necessarily all have to be below the frost line. If the attendant rods get below the frost line, yeah, you should be okay with that, providing it, of course, you do a resistance test and you get a good answer on your resistance test. Next.
Okay, so your next question is, how do you find the sphere of influence?
Okay, that excellent question. I like that. That's what your test is actually doing. You don't know, there really isn't any way to know that ahead of time. You can get some general idea from if you know what the nature of your soil is. If you're in good loam soil in a relatively moist environment, then your sphere of influence is going to be relatively small. If you're out in the desert, if you're in sand or something like that, if you're in Florida, you do have a problem. It's going to be much bigger. But that's actually what your test does. So when you plot the Fowler potential, resistance against distance, and then you can actually see on your graph how big that sphere of influence is. And what you can do there, if you're storing your test results, your first test is going to take you a lot of time, and you might think, oh, darn, uh, I'm taking hours here. This is not good. But your first test is going to kind of, break the ice, so to speak. And then subsequent tests can be done much more quickly once you have this idea of how big your grounding resistance sphere is. And you can certainly simplify your subsequent maintenance test. Okay, next.
Okay, Jeff, can you use a earth clam tester if you only have one electrode?
Yes. The answer to that is yes. But you can also use a clamp if you have a big grid. Uh, we don't have time to go into that technology today, but when we do the webinar, we have one webinar coming up on methods, and we have another webinar coming up on techniques. And the technique webinar will cover the clamp on fully, and we'll answer that question for you 100%. But the quick answer is yes, you can. Next.
Okay. Is the aux potential probe in the 3-point method usually run out 90 degrees from the current probes? And if so, why is that?
Well, shame on me. This is something I've seen a paper on it someplace. I probably have it stored, and I really need to review that. It's a very good practical question. Yes, you may be in environments where you can't go line of sight. If you can, if you're running your test and you're plotting your results, do line of sight if you at all can, because that makes everything much simpler and much cleaner. But yes, you can be in situations where there's trees, bushes, electrical connections of various sorts. So yeah, there can be all kinds of problems in your line of sight. And you do not have to go line of sight. You can run your potential probe off at other angles. And it seems to me, and this is where I'm coming up short in my knowledge, and I really should explore this. I think 90 degrees, I think that's the one that you don't want to use. But I'm not positive about that, and it may be worth searching the literature. But in general, yes, you can go off at other angles It just makes the test not quite as clean, but yeah, you can do that and you can get a perfectly good test at going off at other angles with your potential probe.
Okay. The next question is, in solar sites, sometimes we have very large ground grids. Since testing is dependent on distance from grid, based on the size of the grid, it becomes impossible to test. Is there a way to test large grids when you can't get out of the field of influence?
Absolutely. And we're going to cover that with the webinar on methods. The first one of those, which we mentioned briefly, was slope method. Slope method uses a mathematical proof where if you graphed your full of potential graph and the line keeps going up because the two spheres of influence, test ground and current probe, are overlapping, so that the graph line keeps going up. Somewhere on that line, there is probably a point where the resistance of your test ground stops, and that's what you're looking for, but you can't see it because they overlap. And so the slope method then puts in a mathematical crunch that looks for where that point is. And we will cover that fully when we go into the methods webinar in a week or two. Next.
Okay, and your last question is regarding the fall of potential test. Does this test have any special requirements or considerations if your ground electrode under test is a substation that is in service?
Yes, you can do that. They test substations in service all the time. They do not have to shut them down in order to do the test. I guess a couple of the significant parameters here. Of course, operator safety is a big deal, and interference with the test method is a big deal. As far as operator safety goes, it is a good idea to just use industry standard, safety measures. So you have boots and gloves and a mat or something like that. That's for the possibility that what the utilities call an event occurs while the operator is doing the test. So the test itself is not dangerous, but if a fault current is going to ground while the operator is running the test, then yeah, the test setup can become part of that. So yes, use industry standard safety procedures, and just be careful. Then the other point is, what about interference with your test result? Well, again, the tester is looking for its own frequency, so it should be okay. So yeah, you definitely do not have to shut down the substation in order to do a test, and they do it all the time, and it's just industry standard procedure.
Okay, thank you so much, Jeff. If your question was not answered, just remember that we will get you an answer via email after this webinar is over. Also, I will send out the link to the full page of webinar schedules and registration links if you're interested, since Jeff did refer to a few of those. And thank you so much for coming. And thank you, Jeff, for being the presenter today.
I thank everyone for their attendance.
Bye, everyone.